Hello there. We have a efficiency question here. A water pump is driven by an engine. The pump raises a volume of 0.5 meter cubes of water in 1 minute from a depth of 30 meters. The pump has an efficiency of 70%. So observe here that we have a water pump, and this water pump is basically driven by an engine. And this pump has an efficiency of 70%. So this 70% is actually reflected by the pump. Now we've got the density of water, in which the water is where the pump is actually doing its work. Now look at the question, what is the useful output power from the engine? So there are two different things that we need to take note here. One is basically the pump. The pump has got the 70% efficiency. And the second one, the question is asking about the useful output power from the engine that is being supplied to the pump. Okay, so let's address the obvious. We've got the engine. So this just represent a simplistic representation, and then you've got the pump, and the pump is basically pumping water inside it that is filling, for example, a tank, this water tank. So you got the water filled up here. The volume of the water is basically 0.5 meter cube, whereas the height is basically 30 meters. So when we are dealing with height, so of course we should know that by intuition that we are dealing with potential energy, which is mgh. Okay, so the time is 1 minute. This would be able to use in order to find out the power, because power is basically work done per unit time. So issue here now, if we were to use the gravitational potential energy of the increment or the rise in the water, we don't know what is the mass of the water, but we do know the density of the water, rho. So we can get mass is equals, the definition of density is mass over volume. So we can get the mass of the amount of water is basically rho times the volume. So rho, or the density, will be 1000 kilogram per meter cube, whereas the volume, as stated in the question, is basically 0.5 meter cube. All right. So therefore, we can find out the amount of power that the water pump uses in order to raise that amount of volume of water is basically gravitational potential energy per unit time. So this one would be 1000 times 0.5, which is our mass, times 9.81 times the height, which is basically just 30 meters. This one divided by the time, which is 1 minute, convert it into 60 seconds. So here you can calculate, you get your answer. Let's just use our calculator here. Roughly around 2452.5 watts. Now let's look at what we are trying to answer. It says here, what is the useful output power from the engine? Now this useful output power from the engine is used to initiate the water pump. However, the water pump has an efficiency of 70%. So it is as if 70% out of the power supplied by the engine is being used up to raise the waters. So now what we want is basically the amount of power supplied by the engine. Therefore, we want to know what is the useful. So the useful output power is basically the amount of power that is supplied by the engine for the water pump. But out of all the useful output power from the engine, only 70% is being used because of the efficiency. So here we can know that the useful output power of the engine would be equivalent, or 70% of this amount of power would be equivalent to 2452 watts. Therefore, we can get the power of the engine 2452 watts divided by 70%. So roughly you will get 3.57 kilowatts, where the answer will be B. Okay, so it's a matter of understanding what the question wants, which you need to differentiate. You are dealing with the water pump, yes, but the question is actually asking about the engine, not the pump. So some students would actually be confused or overlook the fact that what they are actually looking for is the useful output power from the engine, which is basically the total amount of power that the pump is actually receiving from. Uh, and that from that amount of power, only 70% is being used to raise the water. So you need to differentiate between the water pump as well as the engine.